Hello everyone, my name is James and I'm a student in Columbia University and this is my final presentation for Applied Deep Learning class. So the problem statement for this project is quite simple. We are provided with cancer cells, right? And we're trying to identify which regions of those cancer cells are cancerous. Um, so the idea behind that is that we can use something like this to potentially help doctors and medical professionals in identifying where the cancerous patches, regions of the cells are. So a lot of the inspiration comes from Google's paper called Detecting Cancer Metastases on Gigapixel Images. So here I'm sort of laying out what I did differently versus what they did. So I utilized two VGG architectures on two different zoom levels. And I'm also using image sizes of 100 by 100 patches with 60 by 60 centers. And just to make things easier, I'm using stride of 100. So I'm using horizontal, vertical flip, rotation ranges, brightness to do the image augmentations to help my classifier generalize a little bit better. And I also use oversampling to balance the cancerous and non-cancerous patches. That is because in our data set, we'll have far more non-cancerous patches than cancerous ones. And also, I am tuning my model using the validation set. So I will try out different architectures, different types of layers, and I will also make the model stop early once it sees that the model is not improving anymore in that validation set. Okay, so sort of the summary is that my model does pretty well. It does pretty well. So it is able to accomplish 85% F1 score, 94% AUC ROC, 92% precision, and 80% recall on test images. And I also tried out four different combinations of zoom levels, data augmentations, and surprisingly, the most simple classifier did the best, which is kind of a bummer because we want the cool ones to do really well, but it did not. So instead of trying to force using a more complex model, I went with the simple model that was doing the best. And at the end, you'll also see a heat map that is generated to help visualize the outputs from the model. So this is my data set. I'm using three different slides. This is my train image, my validation image, test image. And you can see the proportions of the classes. I deliberately chose this train image because it has a lot of cancerous patches, so there's a lot more things that it can learn from. Ideally, we're using all of our data, but that causes a lot of memory issues. So I ended up just using three, and you'll see that it ends up doing perfectly well. So it ended up being okay. So how do we manage the imbalance in our data set? I talked about oversampling. Essentially, what it does is it looks at the cancerous classes and just samples at random from it, right, with replacement. And at the end, you will have a data set that is perfectly balanced. This is sort of an example of a data augmentation. So we do some rotations, some flips. So this is done in such a way is so that our model is able to see, um, our those patches that are in different orientations. So it helps it basically generalize better, right? So this is also explored. So how are we building our models? This is an example output from two zoom level model. So it looks a little bit complicated, but essentially what we have is two separate architectures, VGG architecture models in parallel. Like one makes predictions on zoom level 3, another makes predictions on zoom level 4, and their outputs are concatenated, right? We concatenate the outputs and use those as the features for these final dense layers, and finally we make a prediction at this last layer. And we're using a functional API to accomplish this. But again, the model that we kind of stuck with is a single zoom level model, and it doesn't look nearly as complicated as this. It will have the VGG architecture, it will have some global average pooling layer, a dense layer, and a prediction layer, and that's about it. Again, we're also using early stopping to determine when to stop training. So that's kind of key to help my model not overfit. So if it deems that if it's not improving on a validation data set, it will just stop learning at that point. So here are the results on my model. So these are all the validation results except the second row, which is highlighted, right? Essentially, it does quite well, but the validation data set is much, much harder. It has a lot less cancerous patches, so it does a lot worse in the validation set than the test set. But key thing to point out here is that the uh, multi-zoom model has much higher recall as opposed to precision, which is actually a desirable trade-off. But what we can do is take the better model and change the thresholds so that we can increase the recall. And the end result, right? The end result, you could end up with a much higher F1 with the same amount of recall. So that is essentially what I am going to demonstrate later, right? So again, this is sort of a bummer that our multi-zoom architecture did not do as well as the single zoom architecture, but that is totally fine. We're not going to force the issue and just use the model that is doing the best. Right, so this is an example of the heat map. So essentially we take little patches and we make predictions on it, right? And the predictions that we get is a probability, right? So the higher the probability, the redder, right, the more distinct in color it becomes. So as you can see that our classifier is able to detect very accurately where all the cancerous patches are. This is the ground truth, right? We overlay the mask on top of the cancer patches to see where the cancerous areas are, and it looks almost identical, which is very positive. Here we'll talk about the trade-offs, right? So we talked about that recall and precision trade-off thing, right? So we can actually, what this is showing is that we can get to 100% recall by changing the probability thresholds. We'll lose precision, right? We'll get to 50% precision, but we can accomplish 100% recall. And I think in healthcare fields, this is very, very desirable, right? So that there aren't any patients who has cancer and they go unnoticed, right? That's much, much worse than saying someone has cancer, and turns out that they don't, right? Which is, which is kind of a good news, I guess, in a way. And this is the ROC AUC curve. What this is telling us, you could have very high recall with 20% false positive rate, so that's also desirable. And what this confusion matrix is telling us is that generally we are right? So we make a lot of good predictions, which is on this diagonal, and we want to minimize this inverse diagonal. So as you can see, we're doing well. All right, so what are the next steps? So there's some things that I could improve on our model. So for example, we could try much lower zoom level. So the paper uses, I think, level 2, and maybe even lower than that, actually. I'm not sure, but we could try much lower zoom level. Right now we're using zoom level 3, zoom level 4, which is not nearly as close to the most detailed version. Also, we can try to kind of configure our model a little bit better. So our multi-zoom level did not do as well, but maybe if you configure a little bit better, it can do better. So those are the two things that I would try. But overall, like I feel very good about the performance of the model. All right, so next we'll go through the code. So a lot of this is unimportant. We're just defining some functions, some packages. You can see the images that we're using. These are the masks. These are masks overlaid to the actual image. So all of that is really good. So here is where we are creating these patches. Essentially, we have two for loops in conjunction. Like one iterates through the x-axis, another iterates through the y-axis, and we're making smaller patches. And if the center is deemed to be cancerous, we label it as 1, else we label it as 0. So we do this for all of our images at level 3. We will also do it for level 4, right? So that's what this is doing over here and all this. And there's some data sanity checks here, some assertion statements to make sure that what we're seeing is what we expect. So here, what this is telling us is that only 22% of our patches are cancerous. So that is additionally with the filter. Oh, I didn't talk about the grayscale filter. So we also look at these patches, and if it looks very blank, right? If there's a lot of grays, we're not gonna use that data, right? So after we perform that filter, roughly 22% of our patches are cancerous. So that is not balanced. So we balance it by oversampling. Again, we randomly sample with replacement until it becomes 50-50. So this part is sort of important as well. So the VGG paper, right? The VGG architecture is interesting. It does not divide the images by 255, which is what Session does to normalize the image. Instead, what it does is it subtracts the RGB mean values. So this is, we're just coding the paper and doing exactly what they did so that, we're not taking any shortcuts or doing anything that's incorrect, right? So we're using this pre-processing. This is an example of a patch. This is a cancerous patch. This is a mask that's laid on top of it. So it looks very cancerous over here. Okay, so that's just the mask. We don't need this. So the red region is the cancerous patches. So here's our first model. This is the zoom level 3 model, right? So we have a lot of dropout layers to help prevent overfitting. We have the base, the VGG architecture base, some dense layers, and then finally a prediction layer. So we have to specify the input shape. We're using 100 by 100 images. And we're also using early stopping, right? So we're gonna run this for 20 epochs, but it stops at 10 because the validation loss stops improving. It looks like it's improving. That's weird. Okay, so it didn't improve relative to this validation loss in 3 steps. So we're using patience of 3. So it didn't improve relative to 0.0674, so it stops learning. And these are our validation results. We get about 45% precision, 60% recall, which is all good. I'm just saving down the model just in case if it crashes. It's good practice. What else? So these are the heat maps on top of these cancerous cells. This is the second model that I tried, is a level 3 zoom level with augmentation. So this is how you do the data augmentation, right? And we're doing basically it's early stopping, same thing here, but it doesn't do as well as the model above. Like it has a lower F1 score. So we have 47% F1 score as opposed to 50%. So we choose not to go with this model. Here is an example of a patch. It's the same exact patch, but in 2 different zoom levels. So this is level 3, this is level 4. So you get a little bit more context on the same exact patch by using level 4, right? So, and you can see like this is exactly the same areas, but this one is just a little bit more zoomed out. So we feed that into our model using what's it called? The functional API. All right, so we have 2 separate base architectures in parallel. Each have its own dropout layers, pooling layers, dense layers, right? So here's the output from the first architecture, output from the second architecture. This is concatenated into one model and one prediction. So pretty straightforward. Hard to implement, but understanding is pretty straightforward. So you specify that these are 2. This is level 3, level 4 inputs, and we get 1 main output. This is the architecture. These are the results. So the F1 score is 32%, much lower. This is another level 2, a 2 zoom level model, but with data augmentation. So here we're doing data augmentation. What else? Oh yeah, the F1 score is a lot lower. So I take this 2 zoom level models and I try to ask like, how can I make this better, right? Because it's not doing very well. So the recall is extremely high, which is good, but precision is really low. So that made me think that it is not learning enough about the details of these patches. So I dropped all those dropout layers and I created additional bigger architecture by having more dense layers. And it ends up having, yeah, exactly what I wanted it to do, which is trade off some recall to get higher precision. and our F1 score goes up to all the way up to 38% with those changes. Unfortunately, it still does not outperform our first model, but that sort of kind of points us into a direction of what we need to do to try to improve this model, right? So that's at least like an interesting thought exercise. So here we take the first model, level 3 zoom level model, and then we do some analysis on it. So these are the metrics that are reported in the report. These are the heat maps, ROC AOC curve, precision recall curve. So all very straightforward stuff. So thank you everyone for watching. Thank you for the TA or whoever you're watching. Thank you so much for watching this during your break to grade this project. Yeah, so leave a comment if anyone has any questions. I'll be happy to answer. Thank you.